Let's do a stoichiometry review that's also going to involve gases, but that'll come at the end. So we have four species here. Iron 3 oxide plus carbon monoxide actually yields pure iron, which is one real way we actually can get pure iron from iron ore. And as a result, we also produce some carbon dioxide waste gas. So let's start off with the fact that we have 454 grams of the iron 3 oxide, and we want to convert that from grams to moles. So we're going to use the molar mass to do that. 1 mole of iron 3 oxide has a mass of 159.7 grams. We can cancel out our grams, and we don't want to stop here. We want to keep going because the first question does ask, what mass of iron in grams can we get from 554 grams of the iron 3 oxide ore? So let's keep moving. We're going to put moles in the denominator. Now remember, this blue means moles of the iron 3 oxide here. We want to go from moles of iron 3 oxide to moles of the pure iron, so we're switching over to red. Now, what is the molar relationship here? There's a big 2 in front of moles of iron, and there's a big invisible 1 in front of the moles of the iron 3 oxide. So we can cancel out top and bottom here. And then, of course, we can go one more step because it does ask for the mass of iron. So we can go from moles of iron to grams of iron. And for pure iron, that molar mass is 55.85. So moles cancels, grams does not. And we're going to get about 318 grams of pure iron, which is what's possible to obtain from 454 grams of the iron 3 oxide ore. For the second part of this problem, now we want to find what mass of carbon monoxide is also required for this reaction to even go forward. So we need two things. We obviously need some iron 3 oxide, but we also need some carbon monoxide for this reaction to work. So how much carbon monoxide is required for this to go forward with this much of the iron 3 oxide ore? So we have our same starting material, or the way we start the problem is the same. 1 mole and 159.7 grams. Then we can cancel out top and bottom here. And we're going to keep going with this. We're going to get rid of moles of the iron 3 oxide. But now we're going not to moles of carbon dioxide or moles of iron. We're going to moles of the carbon monoxide. The mole to mole ratio is 3/1. So we have 3 here and we have 1 here. Let's cancel out our units top and bottom. And then we're going to put moles in the denominator because it does ultimately ask for mass of carbon monoxide. So moles of carbon monoxide to grams of carbon monoxide, we have the molar mass given to us as 28.01. You could calculate that on your own if you wanted to. Moles are gone, grams are not, and as a result, we get about 239 grams of carbon monoxide. That's how much is needed. Now let's do the gas stoichiometry problem. As a result of this reaction, we're going to produce a waste gas, carbon dioxide. What volume of carbon dioxide is produced at 127 degrees Celsius and 2 atmospheres? This is going to require knowledge of the ideal gas law. The ideal gas law is PV equals nRT. A useful problem-solving strategy is to list out or somehow check off the things you know from the problem. So, according to this problem, we have the temperature. Now, the temperature is not in Kelvin, which we know it should be. So I'm just going to go ahead and turn that into Kelvin. I'm going to add 273, and that's going to be 400 Kelvin. So that problem was solved pretty easily. And we also have the pressure, which means we have P here. R is just a constant. I can go ahead and tell you right now that R is about 0.0821 liter atmospheres per mole Kelvin. The units aren't particularly important to know, but it does kind of give you a clue about how all of these quantities are connected. So there are two things we don't know. We do not know the moles of N, and we also don't know the volume Matter of fact, that's ultimately what we need to find. So you can do this now or later, but you will need to rearrange the ideal gas law equation to solve for the thing it's really asking for. It's asking for the volume of CO2. So to do that, I'm going to divide both sides by P to isolate V. That's going to give me volume is equal to N times R times T divided by P. And if we just do a double check of what we know R, we know T, we know P, we don't know N, and we ultimately don't know V. So how do we actually get N? What N are we talking about? Well, we're talking about the carbon dioxide. So this is going to be moles of carbon dioxide. So step one, we need to solve as much of the right side of the equation as possible so that we can actually solve for V, which means we need to find moles of carbon dioxide. So the question is, what volume of carbon dioxide is produced under these conditions? And we're still going to be starting off with this material, 454 grams of the iron 3 oxide. So let's do that. 454 grams of the iron 3 oxide. We're going to convert from grams to moles. We know that 1 mole has a mass of 159.7 grams according to the molar mass. And we're going to go from moles of the iron 3 oxide to moles of the carbon dioxide. So let's cancel out things we have so far. Grams are gone, moles are going to be gone. And now we have to use the molar coefficients again. There's a big 3 in front of carbon dioxide, and there's still a big 1 in front of the iron 3 oxide. Now the question is, do I keep going? Would it make sense for me to go from moles to grams for carbon dioxide? No, because you'd be doing too much. It asks for N. N is number of moles, so that's going to give you this right here. So actually, you can just circle the moles and stop right there and do the math. So what we just found was N in our equation. 8.53 moles of carbon dioxide is produced. But that doesn't fully answer the ultimate question, which is what volume of carbon dioxide is produced. So we're going to take this equation and fill in everything we know, which now includes N. So filled in, we have N, we have R, we have T, which is the temperature in Kelvin, and we have the pressure, which is in atmospheres. If we look at the units, all of the units are going to cancel out except for liters, which will be the units for the volume. And this is the answer. We produce 140 liters of carbon dioxide gas if we start off with 454 grams of the iron 3 oxide and we reduce it to produce pure iron under these conditions.